Hello everybody, and welcome to this webinar about building modern applications in the AWS Cloud, together with AWS Advanced Consulting Partner Hostersi from Poland. My name is Marcel van der Vliet, and I work as a Partner Solution Architect at AWS, based out of Finland. I will be your host and moderator for this webinar, and I'm joined today by Adam Smolnik from Hostersi in Poland. Adam is a cloud architect at Hostersi, but he is also an AWS authorized instructor champion and is conducting courses for Cloud Team in Poland. He has been an AWS community hero as well since 2015. Adam is also a co-founder of the AWS user group in Poland, an active speaker at cloud conferences, and he is the co-organizer of the Cloudina Cloud Conference in Poland, which is the oldest community public cloud conference in Poland. Hostersi is an AWS Advanced Consulting Partner and an AWS Channel Partner that is specialized in implementing solutions offered by AWS, server management, DevOps practices, cybersecurity, and performance optimization. They are also part of the AWS Well-Architected Partner Program and can help customers review their workload designs and implementations according to the AWS best practices that are defined in the Well-Architected framework. And Hostersi can then help remediate some or all of the issues discovered during those reviews in order to improve the customer's workload. The learning objectives of today are around the topic of building modern applications on AWS. You will learn about what is called the 12-factor application methodology, which is a methodology for building software as a service applications, and it's created to raise awareness of some of the problems in modern application development, and also to provide a shared vocabulary to be able to discuss those problems. And it also offers a set of broad conceptual solutions to those problems and the terminology. The format is inspired by a book from Martin Fowler called The Patterns of Enterprise Application Architecture and Refactoring. And Adam will, in a moment, give us more insight in the 12-factor application methodology and also how to apply it in practice to build, deploy, and operate highly available, scalable, secure, and cost-efficient distributed applications in the cloud. You will also learn about the AWS services and tooling for modern application development, and you will see a practical example in the form of a demo. So when companies are looking to become more agile, so they can innovate and respond to changes faster, this requires different kinds of applications than what was common several years ago. Applications now need to scale quickly to potentially millions of users, have global availability, manage petabytes or sometimes even exabytes of data, and be able to respond in milliseconds. We call these modern applications. And they cover use cases from web applications to mobile backends to IoT applications to artificial intelligence and machine learning workloads to batch processing, platform as a service solutions, microservice backends, etc. And modern applications are built with a combination of these new architectural patterns, also operation models, as well as software delivery processes. And they allow businesses to innovate faster while reducing risk and improving time to market and lowering total cost of ownership. And for more information, there is a link here on the slide to download an ebook that we have published. So based on our own experience and also by observing and listening to our customers, we identified a set of best practices for enabling rapid innovation. And these aren't prescriptive, they are not meant to be applied in a specific order, they're not a binary, a do or don't type of thing. So you can use them and mix and pick as you like. These best practices help AWS and our customers to deliver better customer experiences. They empower builders to build better customer outcomes and enable safe experimentation while protecting the business and the customer data. They also enable us to identify and address any issues with performance as quickly as possible and creating business agility through business simplification. we can focus on what really differentiates our organizations while lowering costs and reducing risks. We can reuse what we have, we can build faster, we can deploy new features more quickly and more frequently, and shorter time to market. We can increase developer productivity and maximize our use of standardization and automation. Ultimately, what this means is that we can remove any hurdles for getting high-quality software out of the door and into our hands of the end customers in a faster and more secure manner. And now I will hand over to Adam, and he will take you for a deep dive into modern application development and the 12-factor application methodology, as well as we're going to see a demo. Thank you very much.
Hi. Thank you, Marcel. As you mentioned, my name is Adam Smolnik, and at Hostersi I'm responsible for all AWS Cloud projects. Welcome to the webinar. Our topic today is the implementation of the 12-factor methodology to build modern, efficient, and secure SaaS applications in AWS. That is, advanced programming in the cloud. I divided the webinar into two parts. The first, a little more theoretical, is the introduction, presentation, and discussion of the 12-factor methodology in the context of a sample toll registry application. And the second part, practical, is to present a working application and its implementation in the cloud. We will examine the opportunities for implementing the 12 factors in practice on the AWS Cloud. However, before we start, I'd like to point out that the AWS Cloud is a powerful tool mainly created for developers who want to implement global, distributed applications quickly, securely, and efficiently. It gives more power into the hands of developers, but also definitely puts greater responsibility on them for the entire solution. Dear listeners, use the cloud carefully and take advantage of its full potential to create more and more excellent systems. And remember, the cloud is merely a tool. The true value lies in the idea for the application, its architecture, and above all, your code. May the programming power be with you. You not only manage and control the thread or process of the operating system, but also can set up and deploy virtual data center infrastructures with all necessary equipment and resources using your code. Let's return to the main topic of our webinar, the 12-factor application and what it is. It is a methodology for creating distributed systems, most often operating in the cloud in the SaaS model, Software as a Service model. It is also a collection of good practices written by Adam Wiggins. These practices are based on a real-life experience and have been tried and tested in battle by the developers of the Heroku platform. What can we apply these good cloud principles to? First of all, we can use it as a reliable source of guidelines for implementing applications in the SaaS model, which use a declarative way of configuring runtime environments, clean contract with the operating system, native cloud features including serverless, CI/CD methodology, infrastructure as code, and scaling. The targeted group is primarily SaaS application developers and DevOps engineers managing such solutions. Now let's talk about the goals and what all the fuss is about. Well, the use of the 12-factor approach should allow us to have a new developer work on the application promptly, so that the service under construction can be launched instantly on a local or cloud development environment. Secondly, This methodology should reduce the application's dependency on a specific platform, for example operating system, and at the same time make the migration between different runtime environments easier. These 12 factors also carry the promise of a burden-free maintenance on cloud platforms and reduction of differences between runtime environments, for example between prod, test, and dev. On this slide you can see the names of all 12 factors. Before I start discussing each of them separately, let me present the application that will serve as a practical example of using the 12-factor methodology in the AWS Cloud. So let's start by defining the application's business context and requirements. Let's assume we currently manage a system supporting automatic collection of road and tunnel tolls. I had the opportunity to not only see but also to experience the practical application of such a solution in operation when traveling by car through Norway. Moreover, the system we'll be discussing is additionally enriched with the functionality of notifying the relevant public services in the event of a stolen vehicle being detected. Each vehicle is identified based on its license plate. In the scenario under discussion, the current solution doesn't meet at least several important requirements and expectations regarding performance, high availability, and scalability, which in turn causes measurable financial losses, as well as frustration for system users. A prior analysis also allowed to identify two problem sources. The relational database creates a bottleneck and the monolithic structure of the application impedes effective scaling. In addition, it turns out that the OCR module often generates incorrect readings of vehicle registration numbers, which in turn incurs huge administrative costs associated with handling complaints. Also, the library for extracting metadata from photos is obsolete. Its codebase is no longer developed and updated. As a result, the library has become vulnerable to threats. In addition, reusing existing functionalities, for example of the OCR module, is highly problematic due to the monolithic structure of the application. Another factor that cannot be overlooked is the issue of maintaining consistency and integrity of a codebase. For the time being, the codebase is scattered across many repositories due to the use of the copy-paste method, that is copying the module code multiple times to different projects to bypass the monolithic structural limitations. The structure of the current application is a typical monolith. Here you can see the structure of the present Java application. It is a typical monolith that leverages the Spring framework with JARS modules embedded inside the application WAR file. What can we improve here? Let's start with the concept for changing the structure and architecture of the application. First of all, we'll try to replace the external OCR library with a dedicated service to take advantage of additional features and at the same time increase the reliability of our OCR module. Next, we will exchange the Java library for extracting metadata for a more efficient and faster one, but this time written in Python. We will also transform the monolithic architecture of the entire application into microservices, replacing modules with discrete microservices and projects. So let's define a task to be performed. The system needs to be modified or adapted to support the toll collection, detection of stolen vehicles based on license plates, and sending notifications for the events above. When we dig deeper into the details and specification of functional requirements, our system has to store photos of vehicles and their license plates, automatically read and recognize license plate numbers in real time, save image data in a database, search for the stolen vehicle numbers, send information about events, for example detection of a stolen vehicle. When it comes to non-functional requirements, it is essential for the delivered solution to be highly available, scalable, and cost-optimized with the ability to align spending with the load and in proportion to resources being consumed. Besides, the system needs to provide security and redundancy for relevant data. The solution is also to keep personnel costs low regarding system maintenance, operation, and administration. Now it's high time to make decisions. The AWS Cloud will serve as the primary runtime environment. This choice is dictated by many reasons, for example, the flexible payment model in which we pay for actual resource consumption, a broad range of services covering the most or even all of the tools necessary to implement the solution, and a uniform integrated runtime environment is also a huge advantage that makes the development process easier, faster, and more efficient. Another vital decision to make: breaking the application monolith down into independent microservices. That is, setting up disparate projects for each of the modules and separate deployment units. Our microservices will operate in the auto-scaled ecosystem. The microservices themselves don't make up the entire application. For now, they are pivotal, although unbound independent components. We still need a mechanism that integrates, drives, and controls the flow of data among discrete microservices. This missing functionality can be implemented in several ways. For example, we can call services synchronously or asynchronously, one by one, to form a chain of invocations, but it is really nothing more than a distributed monolith. Fragile in nature, sensitive to disruption, and burdensome to debug. I do not recommend this approach. Another, slightly better and more reliable way is to link loosely coupled microservices using queues, for example SQS queues. The queues in this solution mold an intermediary layer and a secure permanent buffer for input and output data being transmitted from individual microservices. It's usually a somewhat better approach than the former, but can we find an even better one? Yes, a much more convenient solution would be a dedicated service that orchestrates the status and data flow among services. We must also be aware that by solving one problem, we usually create a new one. In our case, by transforming the monolith into a microservice architecture, we eliminate the complexity hidden in the monolithic codebase. However, without proper discipline in managing data flows and without using the correct architecture, we can generate a network of complex interactions and interconnections between microservices, which can negatively affect reliability. It can also bring on new challenges in system management. Now it's time for the next decision: how and where to run the application code. In our case, it's a choice between EC2 machines, containers, and the AWS Lambda environment. Considering the fact that our basic business requirements are the maximum reduction of administrative costs, as well as automatic scaling and payment for the actual use of resources, AWS Lambda becomes the natural first choice. When deciding on additional services supporting the application, for example a database, the question arises whether to use services managed by AWS or software installed and managed later by us. Here the choice is much simpler. Based on the requirements, we used managed services wherever possible to be able to focus on development work and providing business functionality of the application. To sum up, we built our solution using AWS Lambda and services managed by AWS to speed up project implementation. AWS services will be leveraged for different purposes and at different stages of the project. The entire solution will be based on infrastructure as code and launched on the AWS Cloud Formation service. We will also utilize the development tools provided by AWS, that is CDK, Cloud Development Kit, and SDK, Software Development Kit. We'll also create CI/CD workflows based on AWS services. Opting for AWS Lambda as the runtime environment has many advantages, but also comes with some drawbacks and limitations that we need to be aware of before making a decision. Notably, the issue of cloud locking or strong dependency on a given cloud environment can often become an impediment. However, it is worth mentioning here that programming in the cloud is still in its infancy and changes occur regularly as the new design patterns are developed and then step by step adopted. The upward trend in cloud expansion seems to be permanent, and present constraints are gradually removed by AWS. The tight dependency can be mitigated by properly implementing the application and by treating AWS Lambda as another runtime environment for executing your business logic and as an event-driven cloud framework for good measure. Extraction and isolation of business logic and placing its code in separate packages or even as standalone libraries for more complex projects can significantly reduce the dependency of our application on a specific cloud platform. Also, in this case, it is crucial to remember that there is no replacement for real tests of our solution in various runtime environments. And here is my recipe for diminishing the uncertainty of tomorrow. Distinct packages solely for application logic and separate ones for code specific to a given runtime environment. A quick glance at the architecture diagram of the solution deployed in AWS. The main players here are AWS Lambda for executing code and step function service that drives data flows. In addition, we also leverage supporting services like Amazon S3, DynamoDB, and SNS. Although the microservices are associated with each other and orchestrated through the step function service, they still fully retain their independence and sovereignty. Communication among them takes place via API, that is a well-defined interface between the service provider and the service client. There are no obstacles to share and expose the OCR service and its functionality to other applications, or even make it available to the public using a separate API gateway service. A few remarks. The architecture presented here does not include parts of the system responsible for authentication, authorization, and steering cameras. Also, to make it easier to comprehend how the entire solution works, the demo application has been simplified, absent of fully fledged logging, suitable exception handling, compensation, and transaction handling. And this is what the actual application looks like, developed with the Step Functions service that integrates particular AWS Lambda microservice functions, which in turn comprise code for the core system functionalities. Now, let's shed light on the structure of AWS accounts. Starting from the left, we have the DC Dev account. The prefix DC here is an abbreviation for Developing Cloud. The DC Dev account is intended for application development and testing. Then we have the DC Prod Production account, followed by the DC Management one as the central place for managing users, logging, and access to other AWS accounts. Next, we have the DC Staging account for pre-production, and finally DC Tools account shared with Dev, Staging, and Prod accounts. The DC Tools account supports and hosts code repositories, CI/CD services, and S3 shared buckets. And finally, we have come to the first factor, which assumes that the application code is always stored and managed in the version control system. In this day and age, most likely this would be Git. Furthermore, the first factor requires each application to have its own single source code repository, and any changes to the code should be tracked and recorded. Nevertheless, the application code can be deployed to many environments, dev, staging, prod, etc. AWS offers a managed highly available Git-compatible service called Commit. As you can see in the screenshot, the entire application codebase, tools for setting up and equipping AWS accounts, including CI/CD workflows, and, of course, the individual microservices code are all stored together in Commit. The second factor deals with dependencies and states that in order for the application to be consistent with this point, implicit dependencies on packages or operating system libraries need to be avoided. The application should also use dependency isolation tools, for example Maven or Gradle in Java or pip for Python. Leveraging such tools simplifies the environment and application configuration for newly boarded developers. CodeBuild is an AWS service used as a part of the continuous integration process that also streamlines the practical implementation of the second factor. The tool allows you to automatically download dependent libraries from external repositories, compile source code, and run tests, most commonly unit tests. The tool outputs application packages ready for deployment. A 12-factor application necessitates the strict separation of configuration from the application code. Oftentimes, configuration data is stored in environment variables. Maybe there is a better and safer way to do it, isn't there? There is, especially in the AWS Cloud as a matter of course. AWS has several services dedicated to this purpose. One of them is Parameter Store, which enables storing configuration data in encrypted form as the so-called secure string that is ciphered with a KMS service key. Secrets Manager is another very convenient service for holding configuration data suited particularly for sensitive or confidential data. Additionally, it is equipped with automatic password rotation mechanisms, for example for RDS service database passwords. The fourth factor focuses on treating services supporting your application as attached resources without differentiating local from external. In the AWS Cloud, resources and services are exposed via public, well-defined API, command line, worth mentioning is the version 2 thereof, and SDK for various programming languages. Users can also take advantage of a graphical user interface in the AWS Web Console. Local implementations for some services are also available. Some services can be accessed using standard protocols. For example, Amazon RDS and Redshift use ODBC, JDBC, Athena JDBC, AWS IoT Core MQTT, and Amazon SES SMTP. Others make use of protocols and APIs compatible with popular open-source solutions. The fifth factor is about the strict separation of the build, publish, and application run stages. Let's recall the basic CI/CD stages: storing and retrieving code for building applications, creating the application package with all dependencies including external libraries, testing, and finally deploying and running it in a given environment. The production deployment usually requires an additional step, namely the acceptance or approval of business stakeholders before taking the actual deployment action. In AWS, we can find a range of services supporting the implementation of the entire CI/CD pipeline. These are the aforementioned AWS Code Commit and Code Build in addition to Code Deploy for application deployments and AWS Code Pipeline for merging particular CI/CD stages. Let's talk now about the application processes and their independence. It is the matter brought up by the sixth factor. A compliant application uses stateless processes to eschew sharing data being stored in memory or on a local file system between processes, threads, or consecutive requests. Leveraging sticky sessions is treated as a violation of this principle. Well, then where should we store the application or user session state or data? Commonly used approaches take advantage of DynamoDB, DynamoDB with DAX, that is with ultra-fast cache, or Amazon Elastic Cache with the embedded open-source Memcached or Redis solution. It is also worth remembering that in the stateless architecture of AWS Lambda, we treat the local file system and memory as a transient temporary cache. The application logic shouldn't hinge on the availability of data stored on a local file system or as static or global variables. Nevertheless, if we have to do it, it is worth adding conditions or if-then statements on variable existence or its expected value as presented on the slide. The seventh factor is all about port allocation and its micromanagement. The essential assumption regarding the application implementation is to have no internal dependencies on other modules hosted on the server. In the serverless approach, the application steers clear of the port management by delegating this task to the runtime environment or cloud service. It uses domain names rather than IP addresses and ports to call the API of other services. Due to the cloud best practices and requirements, I have slightly amended the definition of the seventh factor, which after having been rephrased sounds as follows. Provide services through the API that establishes the exclusive contract with a service client. In the case of AWS Lambda functions, code can be triggered by AWS S3, SQS, SNS services, and many others, including services that provide external access, for example Application Load Balancer or API Gateway. We can also run the AWS Lambda functions directly from its API, SDK, or command line in a synchronous or asynchronous way. Now let's discuss the eighth factor, concurrency. The compliant application must take advantage of processes as basic processing units and various process types for handling specific tasks. For example, one type for fast processing HTTP requests, the other for accomplishing long-running tasks in the background. Horizontal scaling is implemented through process multiplication. Notwithstanding, it doesn't rule out harnessing threads as core processing units. For AWS Lambda, scaling out and in is a built-in intrinsic functionality served automatically by the service. EC2, ECS, EKS or DynamoDB can use a dedicated, purpose-built mechanism that is the auto-scaling service. Disposability is the main focus of the ninth factor. Application processes sticking to this rule can be stopped safely at any point. They also strive to minimize their bootstrap time. In the event of a failure, the processes are supposed to return tasks under execution to a persistent queue for later reprocessing. In AWS, we can shorten the time required to launch an application in several ways, depending on the service itself. For EC2, we can run the application as fully armed or fully baked AMI Amazon Machine Image after creating the image with EC2 Image Builder or other popular tools, for example Packer. For ECS or EKS services, Docker containers start in seconds, while AWS Lambda has a dedicated provisioned concurrency mechanism that can keep the function hot and ready to be executed within milliseconds. Uniform environments are the subject of the 10th factor, according to which a 12-factor application can be safely run on the production as the same tools are used across all the environments to deploy the application. Only minimal differences between the development and production environments exist. For the implementation, we can leverage AWS CloudFormation, a purpose-built service for creating and configuring AWS Cloud resources. CloudFormation uses a domain-specific declarative language for resource definition with extensible syntax that leverages the transformation mechanism under the hood. The service enables consistent and repeatable creation, modification, as well as decommissioning environments. One of the CloudFormation extensions specific for serverless application is the AWS Serverless Application Model with a simplified syntax and easier resource configuration. My latest discovery is the AWS Cloud Development Kit that is high-level, object-oriented framework to model and provision cloud application resources using familiar programming languages and the imperative paradigm of programming. Infrastructure as code in AWS is in its prime. We can start setting up our virtual data centers with the Cloud Development Kit framework and our favorite programming language, regardless of whether it is Java, JavaScript, TypeScript, Python or .NET. By compiling and synthesizing the code of our infrastructure written, for example, in Java, the tool will generate an assembled CloudFormation template. In the next step, we can review and verify resources that will be created, modified and deleted by the CloudFormation service as a result of running the template. This way, we can build advanced logical environments for the production, test and development purposes using the same code base and adjust them to the desired state by deliberately driving execution logic or manipulating input parameter values. And so, we've reached the 11th factor, which is about logs and logging, part and parcel of any fully fledged software solution that gives insight into its performance and helps us troubleshoot the application. The factor requires that the compliant application produces and saves logs in some abstract stream, for example for a dedicated library, framework or third-party service API, for example Log4j, FluentD. It is essential to note the application itself does not manage log files nor their persistence layer. In AWS we have several options to choose from when it comes to the collection, centralized storage and convenient analysis of log content. These are core functionalities provided by Amazon CloudWatch logs with the ability to export logs to other services, for example to S3 with Athena, Elasticsearch with ELK stack for storage, searching and analysis. In case you want to transform and analyze the stream of logs in almost real time, then the Kinesis service family and its tools may prove to be an effective and handy option for implementing such a solution. The last, slightly moot and probably not very congruent to the realities of today's cloud world, is the 12th factor that deals with application management. For an application to be in line with this factor, one of administrative tasks should be run as long-running application processes, operate in an identical application environment and within the same deployment. They also use the same code and configuration. However, these rules and statements raise some questions and doubts. Should administrative tasks be an intrinsic part of the application? Maybe they should be a different mechanism, or an entirely separate entity not tied internally to the codebase of the pertinent application. Would a purpose-built service for environment configuration and administration be better suited for the task? For example, configuration management tools and services, AWS Systems Manager, Chef, Ansible, etc. In the case of serverless applications, administrative and configuration tasks, for example setting up DynamoDB tables or API gateway service, can be implemented through AWS command line, serverless application model framework, including CloudFormation templates, run locally or as part of CI/CD pipeline. Recurring administrative tasks can be efficiently run via a scheduling feature of Amazon CloudWatch Events subservice, and AWS Lambda, ECS and Run command services can be used to execute code or scripts. This completes the theoretical part. It's high time to demonstrate the application I've implemented according to the 12-factor methodology. Let's recall how the toll registry application works and is built. Cameras located at the toll road gates and tunnels take pictures of the vehicle front. Next, the photos are sent to a local intermediary device and then forwarded to a designated bucket in Simple Storage Service. Once the photo is uploaded to the bucket, Amazon S3 automatically triggers the workflow for processing and analysis of the vehicle photo. The registration numbers extracted from the image are saved in the database. A notification is generated if a vehicle with registration numbers matching the stolen vehicle records is detected. The application architecture is based on microservices implemented as AWS Lambda functions, which are orchestrated by the Step Functions service. In addition, the application uses services and resources managed by AWS, the aforementioned S3, DynamoDB, and SNS. Whoops! I would forget about one of the most important services we leverage in the toll registry application, namely Amazon Recognition, whereby we read and extract the license plate numbers based on the vehicle front photos. We will start by presenting how the application itself works and simulate cameras sending vehicle front photos to Simple Storage Service, thereby initiating the entire process of vehicle photo analysis. In this simulation, we will run this process manually using the simple storage service console. However, before we do this, we must sign in to our AWS accounts, which are the runtime environment for our application. For this purpose, I will use the AWS Single Sign-On service, which enables you to define and maintain user account catalog to easily switch between AWS accounts without having to log in again after prior authentication. In a moment, we will use the web console to switch to the DC Dev development account, but before we do this, it is worth mentioning that you can also generate temporary credentials to be used by the command line interface or SDK. You can accomplish this through the SSO website as well. Let's switch now to the development account. I hope you remember that the toll register application uses several important AWS services: Simple Storage Service, DynamoDB, Step Functions, and Amazon Recognition. I will open console windows in separate tabs so that we can easily monitor how the entire application works. Let's take a look at the DynamoDB console. The toll register application, or rather its microservices, use DynamoDB tables to write and store data. Two things to note about the tables themselves. Their names are prefixed with identifiers matching specific services. Hence, the DynamoDB service in the dev environment uses the vehicle register table to save and store the vehicle data recorded by cameras. As you can see at the moment, the table is empty. We will try to change it in a moment. Similarly, the Vehicle Finder microservice in the development environment uses the stolen vehicle register table to record the data on a stolen vehicle, and like the first table, this one is empty as well. Let's switch to the Simple Storage service to send a photo of the vehicle front and thus initiate the launch of the toll register application. I select a bucket and a logical folder dedicated to photos from a given camera and start uploading the photo. As soon as the photo appears in the bucket, the application should start automatically. As you may remember, the new cloud version of the toll register application consists of several microservices controlled and coordinated by the Step Functions service. As you can see on the screen, the service enables you to check the input and output data from individual steps, visually track the program in real time, and store historic data. In our case, the photo processing was successful and no stolen vehicle was detected, so no notification was sent and the notification microservice was not called in this event. Now let's return to the DynamoDB console and check the table content. As we can see, an item appeared in the vehicle register table, that is a row with data extracted from the photo. This comprises location data, GPS data, and the device information from which the photo was taken, as well as the most important element, that is the identified vehicle registration number. Let's now proceed to the test of the stolen vehicle detection option. However, before we do this, we need to add some vehicle information to the stolen vehicle registry table. We will accomplish this using a different tool, NoSQL Workbench, that makes working with the DynamoDB service and tables easier. I will take advantage of the Operation Builder functionality to connect to the DynamoDB console and perform the necessary operations. In this case, adding a record with a stolen vehicle information to the stolen vehicle registry table. Now bear with me while I manually enter the data into the form. The record has been added. Let's now return to the DynamoDB web console and verify if the entry appeared. There it is. Now let's send a photo of another vehicle. While the file is being transferred, we'll be looking into what is happening with our application and its execution. We need to wait a little bit for the application to finish processing. The processing has ended, and this time the system has detected or identified a stolen vehicle. As a result, the notification system should be launched and send out the corresponding notification. As you can see, we received information from the toll register application that a stolen vehicle has been detected. As a side note, I use Workmail, another Amazon service, to handle my email boxes. Time for the final hero of this part of the webinar, Amazon Recognition. Let's check how one of its most important functionalities works, that is, detecting and extracting text from photos. As you can see, the service has detected a large amount of text on the vehicle front, not only the license plate numbers, but also the vehicle make and the dealer data. That's why I had to add custom logic to the OCR microservice to specifically detect license plate numbers. I called it the big box strategy because it searches for the largest area containing text. Now for one last look at step functions. I highly recommend taking advantage of this convenient, useful and easy to use service. With this, I would like to finish the first part of our practical demo in which I showed you how the toll register application works. In part 2, we'll focus on configuring runtime environments and CI/CD pipelines using infrastructure as code. First, I need to switch to my DC Tools account where I keep the code repositories and CI/CD pipelines, and then pick the code commit web console. According to the first of 12 factors, each microservice should have its own code repository, its own codebase tracked by version control system, and simultaneously multiple deployments, dev, prod, test, etc. Taking advantage of the microservice architecture, the toll register application is composed of independent microservices implemented in various programming languages. Here you can see the Vehicle Finder microservice written in Python. Now let's look into the OCR microservice for text recognition in pictures implemented in Java. Let's now switch to the production branch, which I will use to deploy the application on the production environment. Let's take a look at the core of the microservice, that is the OCR Java class. As you can see, under the hood it uses the Amazon Recognition Service, which I have already mentioned numerous times. On the occasion, I would like to mention the second factor of the 12-factor methodology, according to which we should explicitly declare and isolate dependencies, done by me with the help of the Gradle tool, where all dependencies are declared in the build Gradle file. This file will be later used by CodeBuild, which will build a deployment package as part of the CI/CD workflow. A deployment package means compiled code ready for deployment. Let's get back to the code commit service and precisely to the code repository containing the tools project. This project is intended for equipping AWS accounts with all necessary services and resources. Worth noting is that the project is implemented with CDK, Cloud Development Kit. Cloud Development Kit framework is infrastructure as code in its purest form. I leverage it in conjunction with the Java programming language. Let's check the Java code snippet handling the AWS account setup and necessary role configuration. Here you can see the different IAM roles that are required for runtime environments, prod, dev, etc. Now let's check how it builds and configures the CI/CD pipelines. I harness the code pipeline service for this purpose. Here you can observe the individual stages of the CI/CD process and a piece of code that integrates them into one pipeline. You can also see a certain logic in which I separate production environments and add one important stage, that is approval of the deployment before it goes to the production. Here you can also see how to configure CodeBuild to have it build the application packages. To sum up, using this piece of code I set up the entire CI/CD workflows required by the toll register application. Now let's return to the configuration files. Each application has its own, but there is also one common. It is very simple to configure. Each environment has its own name. It also has a separate AWS account. To add another environment, we need to edit this configuration file and insert just 2 lines. In our case, it's a staging environment, and then we can run the Cloud Development Kit framework to add a CI/CD pipeline for each of the microservices of the staging environment. We now return to the code fragment with the CI/CD implementation to show how the code translates to the actual configuration. Once again, these are the individual stages, and finally the piece of code that is responsible for adding the CI/CD pipeline for each of the microservices. Let's compare the CI/CD for the production environment and the development environment. As you probably remember, in the production environment prod, one important step has come: approval. which is not in the development environment. Immediately after the build stage, there is the deploy stage. Let's do some experiment now and see how our CI/CD, that is code pipeline, works in practice. I modify the code from the production branch of the Vehicle Finder service, edit and change the message content, fill out the required fields, then commit and confirm the changes. It is also a good practice and usually a requirement to add some comment. In my case, it's something trivial like change message again. The change has been submitted to the code repository. Let's check what is happening in our production pipeline. It is working and it was started automatically. We don't see any notifications yet. Let's move on to the build stage and take a look what is occurring there. The environment is starting up. Looking at the CloudWatch logs, we can get detailed information about what is happening during the build process. Logs should also be visible in code build. Here they are. This enables us to fully keep track of the entire build process. Getting back to code pipeline, we are still waiting for the build process to finish. Now we can see that the build process has been successful and we are now at the approval stage. That is, we should receive a notification from code pipeline that the service has stopped working and is waiting for our approval of changes. In this demo application, we've implemented the change ourselves, so we are sure it's okay. So let's approve without review. We can see that deployment has started, so let's wait a moment. It usually takes a few minutes to complete. In the meantime, we'll switch to the production account and take a look at the Vehicle Finder microservice code. Let's do it. The pertinent message text has not been modified yet, but we expect that the change we have already committed will be visible right after the deployment is completed. As we have several minutes, I would like to return to the main topic of our webinar, the methodology of 12 factors, in particular the fifth point, that is build, publish, run. The fifth factor requires to separate the build phase from application run. With the support of Code Pipeline and Code Build, I was able to meet the requirements of the fifth factor, clearly separating the various stages of building and running. Let's not forget about the 10th factor that requires dev-prod parity. I achieved this by taking advantage of the infrastructure as code approach using the Cloud Development Kit together with the CloudFormation service. Let's leave theory aside, because the CI/CD process has just completed. Let's check if the change in the code has been deployed to the production environment. I refresh the Vehicle Finder prod microservice and as we can see, the pronoun our in the message has been replaced with the article the, so it did the job. While we're here, I would like to discuss one more factor related to configuration, that is the third factor according to which the application settings should be stored in the environment. As you can see, I fulfilled this requirement by turning configuration values to environment variables, while moving application parameters that require additional protection or security, for example database passwords, onto a dedicated Secrets Manager service. Let's open it and see what it looks like. On the occasion, I would like to point out that the Secrets Manager service is not only a safe place for storing passwords or other sensitive parameter values, but also a rotation mechanism. Let's edit our secret key, modify it, and confirm changes. It works like a charm. Secrets Manager was the last point of our demonstration and the entire webinar. I hope that at least I was able to convince you that implementing applications according to the 12-factor methodology is much easier and more effective using Amazon Web Services.